everybody. We're going to pick up our solving systems of linear equations. So the last video we talked about graphing inequalities, and previous to that we looked at graphing systems of linear equations. Please remember that the solution, the thing we're looking for is, for equations, the point of intersection. And we looked at some vocabulary words: consistent, inconsistent, dependent, and independent systems. Okay, now we're going to get to the algebra part of solving a system of linear equations. So for example, all right, so here's a system. This linear equation and this one. Remember that an equation that says x equals a number is what kind of line? Right, it's a vertical line because that x has a little v in it, right? So remember it that way. Okay. I could graph both of these equations, all right? But actually, there's an easier way if you just come with my bit of logic here. This second equation, x equals -1, is vertical. And every point on this vertical line, the x value is -1. So wherever another line intersects, the x value must be -1. So I can solve this without graphing, which is good for me. By just replacing the x in the other equation with the number -1. I'm going to just substitute into the other equation. So when I substitute for x, it gives me an equation that I can now solve for y. So there's -2. We would add 2 to both sides. Okay, and it's a relief to me that I don't have to graph this, because trying to name this point with one of the coordinates being an improper fraction would be very difficult. So the solution to this system is the point, or the point where they intersect is -1 7/3. So I kind of think this is easier to get to the point of intersection algebraically instead of graphing it. Let's look at another one. So, of course, it's not always as nice as just plugging in one number and calling it a day. But we're going to function in the same process, okay? If we look at this equation here, this is set up for me to substitute. Okay, it doesn't say y equals a number. I'm not just going to be plugging in a number, but I can, in the other equation, plug in or substitute. Instead of y, I can substitute x plus 1. What's that going to look like? So here's 2x plus another way to say y, x plus 1, equals 4. What does that do for me? It gives me an equation with a single type of variable which I can solve. I will combine like terms, subtract 1, and divide by 3. All right, so that's not bad, right? It's actually kind of easy. Of course, it's only half the story. Because of this, I have an x value. I do not yet have the y coordinate. So now I'm going to take that number and plug it in to either of my equations. It doesn't matter. and solve for y. And go easy, right? Doesn't it look like we could just put it right there and we will have y all solved for? So I'm going to solve for y. So the solution to this system is the point 1, 2. That is the point where if I were to graph these two lines, that is the point where they would intersect. Okay, sometimes it's not already set up for us to go ahead and substitute. Sometimes we might have to do a little bit of work before we're able to substitute. What do I mean by that? In that last system, that one variable, it was a y. That y was already isolated. It was already 1y equals. I don't have that situation here. But I can isolate any of these variables that I want. Again, we always want to take the path of least resistance. So if there is a variable that already has a coefficient of 1, that's our best bet. That's the best variable to isolate. How come? What if I isolated these y's? I would have to divide by 2. And what would happen? I'd have 7 over 2. We have fraction work then. We try not to. We're going to try to avoid that. So I'm going to isolate this x here. How do I do that? Subtract 2y. X equals negative 2y plus 7. Okay? All right. Now I'm going to take this and I have to plug it into the other equation for x. So we're going to take this negative 2y plus 7 and put it right here. Now, another complication is that we have a coefficient. And so we're going to have to distribute. So one more time, instead of 2x, it's 2 of these. Negative 2y plus 7. So we have to distribute negative 2y, positive 14. Okay, now we have a little work to do. Combine negative 4y plus 2y. Subtract 14. Divide by negative 2. All right, so we have a fraction. But it's kind of an easier fraction. At least it's not 13 over 31. Okay, so we take this number and we're going to put it into either here or here. Here's the good news. 2 times a half or 2 times a half. That's kind of nice because 2 times a half is 1. So it's going to cancel that denominator. We'll have a nice whole number. I'm going to plug it in here into my first equation because I have a coefficient of 1. I'm running out of room here. Okay, x plus 2 times a half equals 7. 2 times a half is 1. Subtract 1, we get our solution. So the point of intersection is 6 1/2. I'm going to plug. So I generated this solution by plugging this number in up here. I'm going to check my solution by plugging my 2 numbers into this other equation. 2 times 6, 12. Plus 2 times a half, that's 1. 12 plus 1 is 13. And so the check is pretty quick for these numbers at least. And I know that that answer is correct. Let's look at another one. Okay, once again, we want to go the easy route, as easy as possible. So I'm going to isolate this x here because it's got a coefficient of 1 already. So what's that going to look like? Negative 3y plus 5. I have to subtract 3y. Okay, now I'm going to take this and plug it in for x in the other equation. Again, we have a coefficient we're going to have to distribute. So instead of 5x, 5 times negative 3y plus 5. Okay, so we'll distribute negative 15y plus 25 plus 6y equals negative 2. These y's are on the same side. We're going to put them together. Negative 15 and 6. Negative 9. All right, we're almost done solving for our y. Subtract 25, subtract 25. And divide by negative 9. Negative 27 over negative 9. It's not a fraction. This is good, right? Okay, so that's half the story. That gives me my y value. I need to go back and find x. Plug this number in either here or here. Easiest one seems to me to be this one. So x plus 3 times 3 subtract 9. X is negative 4. 5 minus 9 is negative 4. Okay, so our solution is what? Negative 4, 3. Solution. That's the point of intersection. And I'm going to check it real quick, okay? Since I generated this solution by going to the first equation, I'm going to check the coordinates by going to my second equation. So 5 times negative 4, negative 20. 6 times 3, and clearly that works. Okay. 2 more we're going to look at. Let me see what I have here. Okay. So let's look at this system. Once again, we can decide which variable to isolate. This one is sort of all set up, and as I look at these numbers, I can see that they're divisible by 2. So I'm going to isolate this x, and all I have to do is divide by 2, 2, 2. What does that give me? 8 over 2, 16 over 2. Okay, there's my equation. That I am going to replace for x in the first equation. There's no coefficient, or there's a 1, so we don't have to worry about distributing. I'm just going to take these 2 terms and put them here. And I hope you notice something. What happens in this system? The 4y's zero out, and I am left with 8 equals 8. What did that mean when we arrive at a true statement like this? There's no variable left. This doesn't say x equals 8 or y equals 8. It says, hey, 8 is the same as 8. We know that that is true. When we generate a true solution, if you recall, we say that our solutions are infinite. What does that mean in terms of these two lines? These were two versions of the same line. If you were to graph them both, one would be on top of the other. So, sometimes graphically we see that, yeah? Sometimes through substitution we arrive at that same idea because we started with two versions of the same line. So what's the last thing I'm going to show you here? Well, we just finished finding solutions, points of intersection. We just looked at one that is infinite. Therefore, we must be looking at one that has no solution. So let's look at that system. Okay, so I already gave you a heads up that this is going to be no solution. But what happens if you don't have a heads up, if you're just beginning looking at this system and trying to work your way to find the solution? What's it going to look like? So, which of these variables would be the nicest to isolate? Oh, I'm sorry. It's not a y, that should be an x. Okay. Yeah. All right, which of these would be the best to isolate? Not this x, how come? I'd be dividing 5 by 6, 5 over 6, I'd have a fraction. Same is going to happen here if I try to isolate this y. I'd be dividing by 12, so I'd have a 5 over 12. Come down here, what if I isolate this x? I'm going to divide by 4. Oh, 8 can be divided by 4. I'm going to isolate this x. So I would do that by adding 8y, and now divide by -4. 8 divided by -4 is -2. Okay, so that was kind of nice, right? And plus 0, if you want to say plus 0, you can. Not necessary. So I'm going to take this and put it where? Into my first equation, because I did this from the second equation. I have to go back and substitute in the first. All right. I have a coefficient here, 6. Okay. When I do that substitution and I multiply, what happens? Both of these y terms, they're opposites. They zero out. So what I end up with on the left is a big fat 0. There is nothing here. And we all know 0 is not equal to 5. So you will generate a false statement, which tells you that there is no solution. Because if I came back up here and put them both in slope-intercept form, what would happen? They're parallel. The only time there's no solution is when they're parallel. So they would have the same slope but different y-intercepts. Okay? So this is a no solution. I don't want you to say, oh, the answer is that they're parallel. No, I want you to say that because they're parallel, the answer is no solution. Okay? All right. Thank you.